Hi everybody, and welcome to chapter 24, video 1. Now the title says there, Young's experiment. Really the full name is Young's double-slit experiment, but I didn't have room to put that all there, so I didn't. This is coming from section 24.1, but actually this first video, while it will lead up to our discussion of Young's experiment, is not really about Young's experiment exactly. What it does is it goes back to a previous section of the book, refers you back to a previous section of the book that we have not covered, a section on sound, and talks about a very important phenomenon. Okay? And it's a phenomenon having to do with waves. Now, chapter 24 itself is entitled Wave Optics. Okay? And that's really what we'll be doing for this whole chapter. That's why it's called wave optics. All wave optics is this. We've been talking about light as a ray. Just a straight line, right? Moving in a straight line. And light does do that. It does move in straight lines. But there's also something kind of wiggly about it. Okay? Now, light itself does not wiggle back and forth. Okay? It's the electromagnetic field that wiggles back and forth, not the light itself. And I know that distinction is a little vague. But for our purposes, what we need to do is to think about light not just as a straight line, but as a wave moving through space. And it's really not much different than a wave moving on the water. Okay? You got your peaks, you got your troughs, the whole thing moves to the right, the waves move to the right, in the picture here at least, they move to the right. And so that's what you need to think about. Think about the fact that light is a wave and not just a ray. Okay, that's kind of the basic idea to keep in mind throughout this entire chapter. It's got a wavelength, right? Remember the wavelength? It's the distance between successive peaks or troughs, if you want to think about it that way. It's got a frequency. It's got a speed, right? And the speed is equal to the wavelength times the frequency. If the light travels in a vacuum, then the speed is equal to c. But in general, it can be passing through glass, plastic, water, whatever, diamond, and so the velocity changes, okay, when it passes from one medium into another. But this rule always applies. Light is a wave, not just a particle, not just a ray. Okay? So, it's all about the waves, this chapter. And this first little mini lecture here, this first video, video 1, is really going to be about not really Young's experiment, but about a concept we have to get in place before we get to Young's experiment. And that concept is very important, and that is the concept called, let's see, what's a good color? Yellow. Interference. Interference is something that waves do. They interfere. And when they do, we call it interference. I'll draw a picture for you in a minute. You can see how it works. But what I want you to know now, before we even get there, is that interference is a hallmark of waves. Now, by hallmark, of course, I don't mean the cards. What I mean is hallmark meaning it is the sign of, it is the mark of, hallmark of. When you have interference, whatever that is, you have waves. You can't get interference if you don't have waves. Okay? That's what I want you to remember. Now, what is interference? I'm gonna erase this picture here and put up another picture in its place. We've all sort of experienced, I think, we've seen it in one form or another. Probably the most common situation, place where you have ever seen waves, is if you're at the lake, whatever lake that happens to be, or the ocean, and you watch the waves. And here's what you get sometimes. Here's the way I want to draw this for you. Suppose we've got two waves coming towards each other. Okay? Kind of a silly little drawing, but you get the idea. Two waves, waves 1 and 2. And let's say they both have an amplitude A. That is, their height above the flat water is A, the amplitude. And they both have the same height. They both have the same amplitude. And they are moving towards one another. Question is, what happens when they meet? Most things that you can think of, BBs, billiard balls, automobiles, cats, when they meet, they just remain themselves and don't mix. They don't occupy the same space. But waves can occupy the same space. The next thing that happens when they meet, they create a single wave, 1 plus 2, wave 1 plus wave 2, and the amplitude just for that moment is twice the amplitude of either wave combined. They become a single wave. When two cats collide, they don't become a single cat. When two billiard balls collide, they don't become a single billiard ball. But when two waves collide, they become a single wave, just for an instant. And then what happens is the two waves just keep on going, as if they had never met at all. So now they're both back down to height A. Now 1 is still moving to the right, 2 is still moving to the left. They pass right through each other. Now I should have probably drawn this shifted a little bit, but you get the idea, I hope, that the two waves pass right through each other. I think that'll be visible. Yeah, a little dark down there, but you might still be able to see it. The two waves pass through each other. And at the moment they meet, they become a single tall wave. So if you see two waves you're out on the boat or something, two waves come together, all of a sudden you see this peak, and then it's gone. Because the waves have traveled on. Okay? Now a similar thing can happen. I'm going to change pins. That one doesn't seem quite bright enough to me. A similar thing can happen if you have a peak and a trough moving towards each other. So we're back looking at the water again. Peak 1, trough 2. Okay. Let's say this is A. And that's A. So they're both have the same amplitude. Remember, amplitudes are always positive. They tell you how much the wave is displaced from 0. Now in this case, you've got a wave, a peak rather, and a trough. They're both waves, but one's a peak and one's a trough. Now when they meet, if they have the same amplitude and basically the same shape, when they meet, they will cancel out. So that just for an instant, right? These are like 3 frames of a movie. 1, 2, 3. 3 frames of a movie here too. 1, 2. The second frame would look like that. The two waves have canceled each other just for an instant. So if you started the movie on this frame here, all you would see is a flat, calm surface. But out of that flat, calm surface quickly would emerge the two waves. 1 still moving to the right, and 2 still moving to the left. 2 is still a trough, 1 is still a peak, and they have their original amplitude still, but at that point they have amplitude 0 when they meet. Waves pass right through one another. They add, in this case. They subtract, as in this case. The first case is known as constructive interference. because they construct. They add to one another to make a thing larger than either one of them originally was. This case here is known as destructive interference. Because when they meet, I'll look at you right through the middle here, because when they meet, they destruct one another. Okay? They cancel completely. This is actually known as completely destructive interference. You can have partially destructive interference. If the wave 1 was twice the amplitude of wave 2, they would destruct some, but not completely. So if this number were, if this had height 2a, this had depth, pardon me, yes, if this had height, if wave 1 had height 2a, listen closely, if wave 1 had height 2a, if wave 2 had depth a, then when they met, they would make a single wave of height a. That would be partially destructive interference. Completely destructive interference is the case where the cancellation is absolute, as in this case here. Also, if there were two troughs meeting, when they met, it would be just like this, but flipped upside down. When they met, it would make a single trough twice as deep as either one trough. That would still be constructive because the two waves are still adding up to make something bigger than, larger in magnitude than the two things themselves. So if these are, if it's two peaks or two troughs, it's constructive. If it's a peak and a trough, it's destructive. Okay? So this is peak plus peak, or trough plus trough. Either way. In the first case, you get a big peak when they meet. In the second case, you get a big trough when they meet. This case here, for destructive interference, it is always a peak plus a trough. Okay, that's it. That's 12 and a half minutes, which is longer than I wanted to. I'm just rambling on. I like talking to you. It's just what happens. So we'll close up shop here. Next, watch the Veritasium video on, no, that's the third video. So next video down, I'm going to say a bit more about interference, about Young's experiment.